Welcome to this lecture on the topic of building an expert system. During this lecture, we'll start by providing a high-level overview of expert system building. Then we'll discuss different development roles needed to build an expert system. And then we'll move into the area of knowledge engineering, beginning with an overview, moving on to knowledge acquisition and elicitation, then knowledge formalization, and lastly, knowledge verification and validation. Let's start with our high-level overview of building an expert system. Recall from our lecture Introducing Expert Systems that we discussed why we might want to develop or use expert systems to begin with. For instance, when human expertise is in short supply, expertise itself is expensive to develop or to hire, it can be hard to get hold of experts in a hurry, and we can lose experts due to people moving on to other jobs or by passing away. The building of an expert system also serves many functions, including documenting or preserving expertise, reproducing it or making it available upon demand, and teaching and disseminating the expertise. And lastly, expert systems offer expertise that doesn't get bored, tired, frustrated, or scared. Let's start by considering how to choose problems that might benefit from building an expert system. It's important to be realistic about the costs involved and to ensure that the expense is justified, given the expected benefits. Expert systems require iterative development, which is a large investment of time. However, the cost of building an expert system can be justified, especially when expertise is in short supply. Next, we want to ensure that choosing an expert system as a technique is appropriate to begin with. They're likely not very appropriate for problems requiring manual dexterity or physical skill, problems that require a lot of common sense knowledge, and problems that are solvable with simpler techniques, such as flowcharts encoded as a simple program and spreadsheets. In other words, if simple methods already work, don't bother looking for a more complex solution. Expert systems are likely appropriate when a problem requires highly specialized expertise, but at the same time, it would only take a human expert a shortish time to solve that problem. For example, an hour's worth of human time maximum. The reason for this is, as problems get more and more complex, they might be a lot harder to transfer that knowledge into an automated expert system. And lastly, in deciding whether your problem is well suited to developing an expert system, you might want to make sure that there are available and cooperative experts to help you build your system. Further, you might need to assemble a development team, as well as example users to try out your expert system and see if it's user-friendly. Obviously, these guidelines are more targeted towards larger scale and more sophisticated expert systems that might be used at the academic and industrial levels. When deciding whether building an expert system is a worthy investment, you'll want to start with a cost-benefit analysis and include considerations such as, can the problem be solved effectively by conventional programming? Is there a need or desire for an expert system? Is there at least one human expert willing to cooperate in its assembly? Can that expert explain the knowledge to a knowledge engineer? Can the knowledge engineer understand the expert? Is the problem-solving knowledge mainly heuristic and uncertain? And are the time and monetary costs going to pay off? Now let's take a moment to look at the process of expert system building at a glance. Notably, your first attempt is unlikely to work perfectly, as this tends to be a process involving some trial and error. This can be because an expert generally finds it difficult to express exactly what knowledge and rules they use to solve a problem. And also, a lot of knowledge may come from common sense or subconscious knowledge, which might seem obvious to the expert. Thus, they might not bother mentioning it, even though ultimately it will need to be explicitly captured in the knowledge base of the expert system. The first phase of expert system building is always knowledge acquisition. Here, we want to gather or extract relevant knowledge. After this, we move on to the formalization of knowledge, into formally structured knowledge. This is aimed at building the expert system's knowledge base. This begins with implementing and prototyping the knowledge base. This process can involve creating an intermediate representation of the knowledge before moving on to complete formalization, then compiling the knowledge into an executable form that the inference engine can process. For example, this could be production rules. And then checking the system's performance, as well as showing it to an expert or experts to get initial feedback. Then we move on to refinement of the system. This involves iterative development of the knowledge base, building off of this prototype. This is also a point where you might seek to get additional feedback from both the expert as well as potential end users of the system. And lastly, maintenance, as needed, can be an ongoing process involving continuously updating the knowledge base by adding, deleting, or changing rules to keep up with new knowledge or changing circumstances. Now let's move on to discussing the different personnel roles that are generally needed in the development of an expert system. Recall our schematic of an expert system. As we've mentioned, one of the most important people involved in building it is a domain expert. The domain expert works with a knowledge engineer to facilitate the process of knowledge acquisition. From here, the knowledge engineer can work with a software developer or coder who will actually take the engineered knowledge and turn it into an expert system. Depending on the background and skill set, these roles could be handled by the same person, or you could have a domain expert who also has experience with computer programming that can serve in all these roles as well. In addition to a domain expert, a knowledge engineer, and a developer or programmer, the development team often also includes a project manager and an end user. The success of developing an expert system, of course, depends on how well these members work together. Anyone can be considered a domain expert if he or she has a deep knowledge of both facts and rules and strong personal experience in a particular domain. In general, an expert is a skillful person who can do things that other people may not be able to. They have to be able to communicate their knowledge, think through their own internal knowledge and reasoning, and be able to participate and commit a substantial amount of time to the project. Domain experts are arguably the most important member or members of an expert system development team. Then there's the knowledge engineer, who's somebody who's capable of designing, building, and testing an expert system. Their first job is to interview the domain expert to find out how a particular problem is solved. They establish what reasoning methods the expert uses to handle facts and rules, and decides how to represent them in the expert system. The knowledge engineer is also usually responsible for choosing some development software or an existing expert system shell with which to build the expert system. They're also responsible for testing, revising, and integrating the expert system into the workplace. Ultimately, the knowledge engineer will work closely with both the domain expert and the end users. And the domain expert must be able to understand both the domain logic as well as the technical limitations of the shell that's being used, such as clips or drools. Next, we have the programmer. This is a person responsible for the actual programming to describe the domain knowledge in terms that a computer can understand. Often they'll use symbolic programming skills such as Lisp or Prolog, and also some experience with expert system shells would be preferable, again including things like clips or maybe Pike. And certainly they would also need conventional computer science experience in programming languages such as C, Pascal, Java, Python, etc. Further, it could also be helpful for the programmer to be able to utilize generative AI and prompts to generate necessary code, for example using Claude or Copilot. The project manager is the leader of the expert system team. They're responsible for keeping the project on track and ensuring that all deliverables and milestones are met. They'll typically interact with all other members of the team. And then there's the end user. This is a person who represents general users of the expert system once it's developed. The user must ultimately be confident in the expert system's performance and feel comfortable using it. The design of the user interface is a vital component of the project's success, especially for expert systems that are going to be put into mainstream use, and so the user's contribution in terms of feedback here can be crucial. Our next section of the lecture will provide a brief overview of knowledge engineering. Here's a table laying out the basics of 3 terms describing the life cycle of transforming human expertise into machine-readable format: knowledge engineering, knowledge acquisition, and knowledge elicitation. Knowledge engineering is the broadest of these terms, capturing the field, using the entire information ecosystem, and aimed at designing the system architecture and logic on the whole. Knowledge acquisition is a process that can involve human beings, documentation, or data, and this is aimed at collecting clinical guidelines or mining electronic medical health record data in the case of biomedical expert systems. And knowledge elicitation involves techniques gathering information from human experts in particular. For example, interviewing a surgeon to understand their decision-making process. Focusing further on knowledge engineering, this is a broad umbrella term describing the overall field and process of building a knowledge-based system. It's analogous to software engineering, but instead of focusing on algorithms and data structures, it focuses on the representation and application of knowledge. Its scope includes the entire development cycle from planning, knowledge acquisition, choosing a knowledge representation, implementing the inference engine, and testing. The knowledge engineer themselves is the person who acts as the intermediary between the subject matter expert and the computer system. Of note, the acquisition and formulation of knowledge derived from various sources, especially from human experts, can take as much as 70% of an expert system's development time, and many iterations of the refinement of knowledge can be possible. Given that this is such a time-intensive process, automated knowledge elicitation and machine learning techniques have also become increasingly common supplements to the acquisition and engineering of knowledge. It's also useful to consider different possible levels of knowledge analysis ahead of starting to build your expert system. One might be knowledge identification, that could use in-depth interviews in which the knowledge engineer encourages the expert to talk about how they do what they do. The knowledge engineer should understand the domain well enough to know which objects and facts need talking about with a domain expert. Then there's knowledge conceptualization, which aims to find the primitive concepts and conceptual relationships of the problem domain. Or epistemological analysis, which seeks to uncover the structural properties of the conceptual knowledge, such as taxonomic relations or classifications. Or logical analysis, which involves deciding how to perform reasoning in the problem domain. This type of knowledge can be particularly hard to acquire. And implementational analysis, which aims to work out the systematic procedures for implementing and testing this system. Let's review by walking through a simple schematic capturing knowledge engineering in a nutshell. We start with the knowledge source that could include domain expertise, data, problems, or questions. We also have the knowledge engineer, who might employ knowledge elicitation as a strategy to acquire knowledge from human domain experts. Different from knowledge elicitation, knowledge acquisition describes acquiring knowledge from any sources by the knowledge engineer. Once acquired, the knowledge engineer works to formalize this knowledge into structured knowledge in the form of a knowledge base. Here we have a general timeline illustrating a knowledge-based system development life cycle. It begins with planning and formulating a work plan, and then defining the knowledge that will be needed and collected, identifying sources that are needed, and going about its acquisition and analysis. Then it moves on to knowledge design, starting with the knowledge review, so that it will define knowledge, leading to a preliminary data review, and ultimately the formulation of a detailed design before conducting a knowledge system design review ahead of implementation. At this point, the system code is implemented and checked out, leading to a test readiness review. Then it moves on to knowledge verification, involving formal tests and test analysis, leading to a test audit review. This timeline concludes with complete system evaluations and a final review before the system is ready for use or deployment. In our next section, we'll continue on the theme of knowledge engineering with focus on knowledge acquisition and elicitation. Knowledge acquisition is the specific phase within knowledge engineering dedicated to gathering the information needed for the system. In other words, this is the input stage of the process. As noted, knowledge acquisition is a subdiscipline of knowledge engineering. Knowledge acquisition can involve many sources, including gathering knowledge from human experts, such as doctors, lawyers, engineers, or investment analysts, text sources, such as medical journals, clinical guidelines, textbooks, and the web, data mining, where patterns can be extracted from structured and unstructured data sources, or databases, such as electronic medical records, and other machine learning strategies, such as automated extraction of if-then rules from datasets, which could be achieved using algorithms like Ripper. The main goal of knowledge acquisition is to collect all the raw domain knowledge necessary to solve the problem at hand. The typical information that will need to be gathered includes vocabulary or jargon, conceptual concepts and facts, problems that commonly arise, and the solutions to problems that occur, as well as skills for solving particular problems. If knowledge is to be acquired from other sources like databases, datasets, or the web, we might need to go about information extraction. This is the process of extracting structured information from unstructured, machine-readable documents. For example, we have an illustration starting with a selected source, and information extraction could include tokenization and normalization, named entity recognition, instance extraction, fact extraction, ontological information extraction, and many other possibilities. Of note, the process of information extraction could also be further facilitated by modern natural language processing and generative AI techniques. On the last slide, we mentioned named entity recognition, which is the process of finding instances of entities, in other words, people, cities, organizations, dates, etc., in text. For example, we have this sentence: Elvis Presley was born in 1935 in East Tupelo, Mississippi. Named entity recognition focuses on extracting the informative entities in this natural language text, such as here the name Elvis Presley, the year 1935, the city East Tupelo, and the state Mississippi. So imagine we want to extract information about disease outbreaks from a document. We might first scan for named entities, such as dates, locations, and disease names, and then convert that raw text into a formatted set of variables. In this case, looking for dates where a specific disease appeared at a specific location. This can be automated by some kind of information extraction system, allowing us to grab the relevant information from the text and put it into our new database. Now let's move from knowledge acquisition to knowledge elicitation. Knowledge elicitation is a specialized subset of knowledge acquisition that refers specifically to the process of extracting knowledge from human experts. This is considered to be a difficult task because human experts often have tacit knowledge. In other words, things they know how to do but can't easily explain. The knowledge obtained by knowledge elicitation is usually stored in some form of human-friendly intermediate representation prior to downstream formalization. And of note, elicitation is considered to be a form of acquisition, but not all acquisition is elicitation. Framed in the context of knowledge elicitation, we have something called the knowledge engineering paradox, which notes that the more competent domain experts become, the less able they are to describe the knowledge they use to solve problems. This is because experts tend to state conclusions and reasoning in broad terms. Experts make complex judgments rapidly. Also, experts cannot always easily articulate steps to problem definition and solution, and experts often rely on intuition or hunches. When it comes to capturing tacit or implicit knowledge, there are several useful techniques to go about acquiring it. We have interviews, which are structured or unstructured sessions between engineer and experts. Then there's protocol analysis, involving tape recordings of the expert while they think aloud in performing their role, and later analyze this recording, where the engineer breaks down their accounting of the protocol into the smallest atomic units of thought and let these become operators. Another strategy is participant observation, where the knowledge engineer acquires tacit knowledge through practical domain experience with the expert. Or card sorting or laddering, which are methods used to understand how an expert categorizes concepts or prioritizes decisions. And machine induction, which can be useful when the experts are able to supply examples of results in their decision-making, even if they're unable to articulate the underlying knowledge or reasoning process. Which of these are best will generally depend on the problem domain and the expert that the knowledge engineer is interacting with. Some other knowledge elicitation strategies include observation of tacit knowledge, motor skills, component tasks, task constraints and requirements, and knowledge verification. Also, interviews, where unstructured interviews are generally free form, where neither party knows the path in advance, and this approach can be best for exploratory elicitation. Also, structured interviews, which follow a predefined format, take a systematic approach, and are best for detailed knowledge elicitation. Another knowledge elicitation strategy could include process tracing, which could be verbal reports, including simultaneous self-reporting or retrospective recall, or nonverbal reports, such as observing eye movements or gross fine motor movement repertoires. Another might be protocol analysis, including content analysis, discourse analysis, or grounded theory. Or decision analysis, including statistical modeling or economic analysis. Furthermore, we have conceptual techniques, where we represent structure of domain knowledge. This can accommodate multiple experts, but it can be too generalized and can often overlook situation-specific knowledge. And lastly, other methods might include repertory grids, queue sorting, event co-occurrence probabilities, and structural analysis such as multidimensional scaling. Next, we'll move on from knowledge acquisition to knowledge formalization, Here we have another figure that relates to the process of going from acquired knowledge to an expert system with structured and formalized knowledge. This can include identification of problem characteristics to identify requirements, and then conceptualization, where we aim to find concepts to represent knowledge, and then formalization, where we design a structure to organize knowledge, then implementation, where we formulate rules to embody knowledge, and lastly, we would test these rules to validate their functionality. As I mentioned, this can be an iterative process, so refinements can include updates to the formulated rules, and if testing is still not satisfactory, we can do redesigns going back to the formalization itself. Or in some cases, there may be a need to go back and reformulate the problem, going all the way back to conceptualization or even identification in order to tackle the problem at hand. Expert system construction was primarily a trial and error process that involved knowledge engineers, where once they had knowledge from experts, they would fill in their knowledge base and test it out. By the end of the 80s, it was discovered that creating an actual domain model as an intermediary was the way to go. In other words, build a model of the knowledge before actually implementing anything. This can be an intermediate model of some kind that might, for example, be a dependency graph of what can cause what to happen, or an association model, which is a collection of malfunctions and the manifestations we would expect to see from those malfunctions, or a functional model, where component parts are enumerated and described by function and behavior. However, in later years, the emphasis on how to go about developing an expert system began changing to using techniques such as knowledge acquisition tools, or CADs. Here, domain experts enter their knowledge as a graphical model that contains the component parts of the item being diagnosed or designed, their functions, and rules for deciding how to diagnose or design each one. An intermediate representation of knowledge is a structured representation of the knowledge that is not yet in the form of code that can be put into an expert system's knowledge base. As alluded to on the last slide, we could form an intermediate representation using problem decomposition into an AND or graph. This is a technique for reducing a problem into a production system, and as you'll see, it has a number of similarities to a decision tree. Here, the principal goal is identified, and it's split into two or more sub-goals, which are subsequently split further. A graph is drawn of the goal and sub-goals. Each goal is written in a box called a node, with its sub-goals underneath it, joined by links. The leaf nodes at the bottom of the tree are the boxes at the bottom of the graph that don't have any links below them. These generally represent the pieces of data or facts needed to solve the problem. Let's walk through an example of problem decomposition by creating our own and/or graph. We're going to start by placing a box at the top representing the goal, in this case to advise the user of an investment, or investment should be X. So now let's say that we have three possible options for recommendations. Here the investment could be in savings, stocks, or some mixture of the two. Perhaps the information we need to recommend putting it into savings is to check whether savings are inadequate. In other words, if they're inadequate, we should put more into savings. When it comes to stocks, we'll have to check two things because we have an AND branch here, indicated by this arc. So in this case, we'll recommend stocks if savings are adequate and income is adequate. Then, for recommending a mixture of the two, we also want to check two options, whether savings are adequate and if income is inadequate. We can continue to build the tree further to decide whether these nodes are true or false. For example, we might check if income is inadequate by looking to see if the income is below some value W, and whether the income is not steady. In this illustration, boxes in green indicate a point in the graph where input is needed from the user, as facts. So in this case, we need to know whether the client's income is not steady, and we need to know their income to compare to W. Using this and/or tree, we can now identify relationships that will become production rules. For example, in this part of the tree, we have the recommendation of stocks for X. This decision is based on whether savings are adequate and income is adequate, so we can formulate the rule, if savings adequate and income adequate, then X is stocks. Here's another example where we can derive the rule, if income is less than W and income is not steady, then income is inadequate. Or here, if amount saved is less than Y, then savings are inadequate. And for our major goal, if X is savings, or X is stocks, or X is mixture, then advise user investment should be X. This means that the corresponding advice will be given whenever any of these options are satisfied in the rest of the tree. Now here's a slide giving just a little more information about CADS, which stands for Knowledge Acquisition and Documentation Structuring. This can help automate the process from intermediary knowledge to formalization, where the expert provides the model through the CADS rapid prototyping approach, which builds the knowledge base using that domain model. When using a system like CADS, the inference engine can be an off-the-shelf option, or something tailor-made, or some combination based on the engineer's choice of knowledge engineering. Now that we've acquired and formalized our knowledge, it's time to implement our expert system. This is where the knowledge engineer or programmer codes the knowledge explicitly into the knowledge base, formulating rules to embody knowledge. Implementation of an expert system can rely on declarative or functional programming languages such as Lisp, Prolog, and Miranda, which were often first choices for implementing rule-based AI systems like expert systems. This is because the syntactical structure of the rules, as written in these languages, can be closely matched to a chosen form of knowledge representation, and the means by which a query is resolved to a related model of reasoning. A declarative program is a sequence of facts and rules with a set of conditions that describe a solution space. There is some dependence on the order in which these are written, but not nearly as much as in procedural programs. Alternatively, an expert system could be implemented as a procedural or imperative program, consisting of a sequence of commands. Here it's necessary for the programmer to think carefully for each new problem about the steps that must be carried out in order to solve it, and the order in which they must be done. Neural networks are an example of a number crunching application that are typically implemented in procedural languages such as Java, C, or C++. Lastly, when it comes to expert system implementation, we want to choose an expert system development tool, which could include the expert system shells we previously discussed in a previous lecture. And in doing so, we consider the cost benefits, the technical functionality and flexibility of the tool's compatibility with the existing information infrastructure, and the reliability of and support from the vendor. At this point in coding the system, a major concern is whether the coding process is efficient and properly managed to avoid errors. We may need to calculate and implement the certainty values of rules and facts. And depending on the system, we might also need to determine the priorities of rules. Finally, after implementation, we can move on to evaluating our system. This is where we'll talk about verifying and validating the system. In this last section of the lecture, we'll discuss verification and validation in knowledge engineering. Recall this schematic that we walked through earlier. We've now reached the far right-hand side, or the topic of testing. It's important here that we ensure the efficacy of our system before deploying it for real-world use. Verification aims to ensure accurate knowledge representation, asking questions like, are the rules in correct form, or am I building the product correctly? Related to this is validation, which seeks to ensure that the system performs its intended tasks. In other words, is the underlying knowledge correct? Do the rules lead to a correct answer? And am I building a correct product? Focusing on knowledge verification, this aims to examine what the system is supposed to do versus what it's actually doing. We want to see if the system has any errors introduced during programming. You can think of this as being similar to software verification. One of the things we can check with verification is whether we have deployed a system that is compliant with any specifications that were given for the system's development. For example, do we have the proper knowledge representation, reasoning technique, external interfaces, or user interface? And also, does the explanation component of the system work correctly? And does it meet any security specifications? Also in verification, we might search for developer-induced errors, such as redundant rules, conflicting rules, subsumed rules, circular rules, unnecessary if conditions, dead-end rules, missing rules, and unreachable rules. Now switching over to knowledge validation, this focuses on the source of knowledge and ensuring that the knowledge is correct. Methods for this can include protocol analysis after elicitation, comparison of knowledge across multiple experts, inter-expert validation, field testing, subsystem testing, and sensitivity analysis. On the topic of consistency of a knowledge base, a rule base is considered to be consistent if none of its assertions conflict with any initially meaningful fact base. Differently, a rule base is considered to be inconsistent if any rule firing introduces an assertion in conflict with the initially meaningful fact base. Some other considerations in building an expert system might be considering different approaches to conflict resolution mechanisms, or implementing a truth maintenance system, which can be useful when reasoning with defaults and beliefs is requested. Truth maintenance systems are also referred to as reasoning maintenance systems or belief revision systems. These basically maintain consistency between the old believed knowledge and the current believed knowledge within the knowledge base through revision. If the current believed statements contradict the knowledge in the knowledge base, then the knowledge base becomes updated with the new knowledge. One word of warning is thinking about the potential for rule interactions. When you're attempting to expand an expert system by simply adding more rules, this can end up being dangerous to its functionality. Specifically, unexpected rule interactions are liable to happen. For example, you might add new rule conflicts. The need to consider all possible rule interactions makes large rule-based systems unwieldy and hard to update. Also, while non-computer specialists may find it easy to grasp the meaning of individual rules, they often don't find it easy to grasp these issues concerned with rule interactions. Another thing to be cautious about is the possibility of knowledge decay. This is particularly important in dynamic domains. For example, in fields like precision medicine, where new clinical trials, drug approvals, and genomic discoveries can occur weekly, and as such, a static knowledge base can quickly become obsolete. Expert systems could also be considered to be brittle. In other words, they perform well on standard cases, but may fail catastrophically when encountering edge cases or unusual patient profiles that have not explicitly been coded into the original rules. Then there's also the qualification problem. Here we note that it's nearly impossible to define every exception to a medical rule, and as the system grows, adding one new rule to handle an exception may unintentionally conflict with hundreds of existing rules. Lastly, on the topic of expert system maintenance, keep in mind that an expert system knowledge base may need to be continuously updated by adding, deleting, or changing rules to keep up with new knowledge and changing circumstances. This could be facilitated with knowledge auditing and version control, involving regularly scheduled clinical reviews where human experts verify the accuracy of the rule base. The system could also implement versioning, like software code, to allow for rollbacks of new knowledge updates that may have caused reasoning errors. One thing that can help with maintenance is ensuring modular knowledge representation, specifically designing the knowledge base into atomic modules that are smaller, independent rule sets rather than one massive interconnected web, in order to make it easier to update just one area of the system, for example, focusing on a specific cancer subtype without breaking the entire system. And while not necessarily easy to achieve in practice, expert systems could be integrated with data pipelines. Some modern systems use knowledge graphs to automate parts of the maintenance process by pulling updated facts from public medical databases like PubMed. To summarize this lecture, expert systems can take a lot of time investment and expertise to build, so consider your target problem fit as well as the cost benefits before implementing. The team needed to build more complex expert systems generally include domain experts, knowledge engineers, programmers, a project manager, and end users to provide feedback. Developing an expert system generally requires planning, knowledge acquisition, knowledge formalization, prototyping, refinement through validation and verification, as well as the possibility of long-term maintenance to ensure its utility. Knowledge engineering, acquisition, and elicitation are all aspects of building a knowledge-based system like an expert system. And some modern strategies can be utilized to facilitate the process of developing and maintaining expert systems. I'm Ryan Urbanowitz, and thanks for joining me for this lecture. Stay skeptical, curious, and creative.